In the Nevada desert, a Peterbilt tractor speeds forward at a steady 120 kilometers per hour. Its long metallic nose reflects the scorching sun, slicing incoming air currents in two as if a blade were parting the wind itself. Across the Atlantic, a MAN TGX weaves through the ancient streets of Florence, Italy. Its cabin appears almost flat, as though abruptly cut short. The front axle sits directly beneath the driver's seat, and every tight corner becomes a live demonstration of Euclidean geometry. Why do two machines built for the same purpose, moving cargo, possess such radically different bodies? The answer lies not in aesthetic taste, but in a negotiation between torque and turning radius, between collision physics and urban law. Every curve of steel is shaped not only by aerodynamics, but by formulas, limits, and historical trade-offs engraved into transportation systems. In Europe, where even paving stones carry Roman echoes, space is a scarce resource. Regulations limiting the total truck length to 18.75 meters turn every millimeter into a zero-sum equation. Add 10 centimeters to the cabin, and you lose 10 centimeters of cargo space. The result is the cabover design, a flat-faced truck where the driver sits almost directly above the front axle. Nearly the entire remaining length is reserved for freight. In contrast, the United States passed the Surface Transportation Assistance Act of 1982, removing total vehicle length restrictions and measuring only the trailer. From that moment, cabins were liberated from geometric constraints. American engineers extended the nose forward, creating the long hood conventional design. Space, once a shackle, became a canvas for creativity. If Europe designs trucks like a game of Tetris squeezed into medieval streets, America paints vehicles across vast deserts, machines that can stretch themselves along endless highways. In mechanics,
by extending
space
the
is
nose
not
here,
merely length,
we significantly
it is the right to
reduce drag.
occupy volume. And
Let's stretch
sometimes,
it another 12 inches
that right is
and see
granted
the
by a
airflow
political
impact.
signature. A truck is not just a moving box. It is a complex mechanical organism where wheelbase determines the character of the entire machine. American trucks feature extended wheelbases, often exceeding 7 meters, producing remarkable directional stability. On straight interstate highways, longitudinal torque is minimized, allowing the vehicle to glide forward like a train on rails. European trucks shorten the wheelbase by roughly 1 meter, shifting the center of mass forward. This configuration is born to survive labyrinthine streets, tight corners, narrow roundabouts, crowded loading bays. Ackerman's steering geometry, the principle that optimizes wheel angles during turns, is pushed to its limits. If American highways resemble a symphony of straight lines, European streets are a tangled composition of curves. Two worlds produce two opposing kinematic solutions. Yet both obey the same law. Stability is never free. It is always traded against maneuverability. And vice versa. Put yourself in the driver's seat, and physics becomes something you feel along your spine. In a cabover truck, the driver sits almost directly above the engine and front axle. Every vibration, every shock from the road travels through the metal frame into the body. According to NVH noise, vibration, and harshness studies, vertical acceleration spikes can reach 0.8 G during short impacts, enough to cause fatigue after only a few hours of driving. In American long-nosed trucks, the driver sits between the axles. The extended cabin acts as a natural suspension, absorbing oscillations through frame length and structural flex. The experience becomes smoother and quieter. With the engine positioned farther away, the cabin feels almost like a spacecraft cockpit. Comfort, in mechanical terms, is not leather seats or climate control. It is the reduction of mechanical energy transmitted into the human body. In a world of vibration and acoustic waves, the human body is the most sensitive sensor and the most fragile component. When a collision occurs at 100 kilometers per hour, a 40-ton truck carries kinetic energy approaching 150 megajoules, comparable to the explosive force of several kilograms of TNT. That energy must dissipate within fractions of a second. On long-nosed designs, roughly 2 meters of metal at the front serve a purpose. They form a sacrificial zone. The steel structure deforms progressively along the impact axis, dispersing energy before it reaches the cabin. In every crash, the nose dies so the driver might live. European trucks, constrained by length regulations, lack that privilege. Instead of extended crumple zones, they rely on optical avoidance, direct downward visibility toward the road. The flat cabin allows drivers to see obstacles just centimeters away, emphasizing prevention rather than endurance. Where American engineers designed to survive impact, European engineers designed to avoid impact altogether. Two approaches, two ethical philosophies of mechanics converge on one. Principle form follows function, and function follows physical law. Seen from above, every truck becomes a diagram of the environment that created it. America, with open space, vast highways, and flexible regulations, produces long-nosed giants, proud and stable like ocean vessels. Europe, shaped by narrow streets, strict rules, and cultural heritage, produces machines compressed for efficiency in every centimeter. From a mechanical perspective, these are two ways humanity negotiates. Limits one expands the frontier. The other optimizes within constraint. From a philosophical perspective, they represent two definitions of freedom. For Americans, freedom is the empty road ahead to accelerate into. For Europeans, freedom is the ability to maneuver within boundaries. And when steel, aerodynamics, and law merge together, they tell a story not only about engineering, but about how societies choose to survive within the physics of their own world.